So hello everybody. Thank you for coming. As Catherine said, my name is Rose Shepherd and I'm a PhD student at Newcastle University, where I work with Dr. Chris Harrison. Today, I'm going to be talking to you about my research project, which is all about using sound to search for hidden black holes. So, oh, there's a lag with the PowerPoint. Here we go. I'm going to be giving you a whistle-stop tour of lots of different things today. But I'm going to start by introducing a method of exploring data using our ears. And then I'm going to introduce the hidden black holes that I'm looking for and explain how we can study them using something called spectroscopy. Then I'm going to talk about how these all tie together in my research. We are all blind to the universe. And now I'm going to explain what I mean by that. So if we go out on a clear night in the UK, we might be lucky if we see 100 stars, maybe if we're in a dark sky park, 1,000 stars. But many of us live in areas with lots of light pollution. And even so, these stars are just a tiny fraction of the hundreds of billions of stars in our Milky Way galaxy. We need powerful telescopes to get a sense of scale of the universe, such as the Hubble Space Telescope here. So this is an image of a galaxy called Centaurus A, which is taken by the Hubble Space Telescope. And you can see the spiral arms of the galaxy and a halo of stars extending from the center. But there's actually more than meets the eye with this galaxy. So this image is just the visible light, which is the light that we can see with our eyes, the colors of the rainbow from red through to violet. And this is only a tiny fraction of all of the light that there is. As you can see, it makes up a really small part of the entire electromagnetic spectrum, which includes microwaves, radio waves, infrared, ultraviolet, X-rays, which are all light with different wavelengths. So really, we can't see very much at all with our eyes. Now, it's important that we don't forget about the non-visible light if we want to understand the universe. So we're going back to our galaxy Centaurus A, the galaxy I showed earlier. And if we look again with different telescopes that can observe the light that we can't see with our eyes, we can see there are these huge radio jets perpendicular to the spiral arms of the galaxy. There's also a lot of X-ray radiation along the same axis and infrared light coming through what we saw as dust in the visible light images. So you can see the different components of this image on the right. And these are in colors purple and red and pink. And these are just fake colors that someone's chosen to represent these wavelengths of light that we can't see with our eyes. But it shows there's so much more to this galaxy beyond the visible light. But that's not all. Most of the universe is completely dark, and today's lecture is not about the mysteries of dark matter and dark energy, but it is relevant in this context because our understanding tells us that everything we know in the universe, everything we're made of, what stars are made of, what your table, your computer is made of, makes up less than 5% of the universe. The rest is completely dark. It emits no light, and it doesn't interact with light in any way that we understand. So, as I said at the beginning, we're all blind to the universe. It's almost completely invisible to us. So why then are we always using visuals? Astronomy relies on images, graphs, and charts, but there are other ways that we can explore and communicate data. In comes sonification. Sonification is the process of representing data with sound. And this might sound a bit abstract to you, but you might have heard of visualization, which is where we represent data visually, using scatter plots or bar charts or pie charts, for example. Sonification is just like this, but using sound to represent the data. So you might know some examples of sonification without realizing it. So a common example is a Geiger counter, which is used to detect and measure radiation, which produces clicks to represent the radiation levels. Also, maybe you've been in a car which has parking sensors. So here, the distance to the surrounding objects is what's being sonified. So these are some everyday examples of sonification, but I'm going to show you how we can apply this to astronomy data. So here we have a simple example where we're sonifying the planets in our solar system orbiting the sun. So this demonstrates how we can use different parameters of sound to represent different data parameters. Here, each planet is represented by a different instrument and a different note. So the pitch of the note represents the mass of the planet. So those with larger mass, like Jupiter, have low notes, and those with smaller mass, like Mercury, have high notes. There's also a low-pitched note for the sun, which you'll hear at the beginning. So the great thing about our ears is we can hear panoramically, and you can use the spatial location of the sound to represent the movements of the planets in this example as it orbits the sun. If you have stereo on your computer, we'll see if it comes through the Zoom. So you might be able to hear the planets orbiting around you. So let's have a listen to this.
Adding Mercury, one orbit in just 88 Earth days. Next, boiling hot Venus. Our home, the Earth, 365 days for one orbit. Mars, the red planet. Giant Jupiter. Next, ringed Saturn. Adding the side-spinning Uranus. And finally, freezing cold Neptune.
So I work as part of a project called Audio Universe, which is led by Chris Harrison and James Traford. And that clip was part of a Planetarium show, which we made using sonification to explore the solar system. And this was designed with specialist teachers and members of the blind and vision impaired community, with the aim that it would be enjoyable and understandable regardless of your level of vision. And we evaluated the show, and it demonstrated that all audiences, blind or sighted, found the sounds useful and enjoyable, which fits with the idea of universal design, which is when you make things accessible, you make them better for everybody. We can use other senses to help make astronomy accessible. So here you can see we've run school workshops using tactile models of planets and other objects in the solar system and in the galaxy. So children can use their sense of touch to explore the universe. And using sonification and tactile resources just gives more ways for everyone to access and engage in astronomy and other science, which is incredibly important, I believe. So, a quick clarification about sonification. You might be thinking, but wait, you can't hear sound in space. And you're right, sound can't travel through space. So just to clarify, when we sonify data, we are making a representation of the data using sound. Just like that multi-wavelength image I showed you with X-ray and UV light and purple and red, you choose the colors. We choose how to represent the data with sound. We are not putting a microphone in space and listening to the stars. So we know sonification is great for accessibility and communication, but can we apply it to help us with a real astrophysics research problem? And this is something I'm fascinated by because I'm a musician as well as an astronomer. So I really wanted to combine these two things that I love to see if we can use our ears to tackle a science problem. There are actually lots of reasons why our ears might be good for analyzing data scientifically. We're very good at detecting and perceiving information with our ears. So, for example, we can hear a huge range of different frequencies and distinguish between them. With our ears, we can hear a range of 10 octaves, which is 10 doublings of frequency. And I've visualized that for you with the piano keys. But the equivalent light frequencies that we can see with our eyes is equivalent to only 1 octave. So you can see it's a much smaller range. We can detect really quick changes with our ear down to 1 microsecond, which is just a millionth of a second. And as I mentioned before, our ears are panoramic, so we can locate sounds in space around us. And they're always on. So they're good for monitoring sounds whilst we perform other tasks. So like with the Geiger counter I mentioned earlier, you can monitor the radiation levels. Another useful skill that we have is we can pick out signals from a noisy sound. So this is called the cocktail party effect, and it's the brain's ability to focus in on a single sound in a noisy environment, like being at a party. So why might sonification be relevant for astronomy research? We're currently in an era of big data in astronomy. We have exciting new facilities, both telescopes on the ground and in space. Like you see here, I've got the James Webb Space Telescope and the Euclid Space Telescope. And so, as I said, it's a really exciting time, but these facilities are producing huge volumes of data. So the Vera Rubin Observatory, which you can see on the bottom left, captured its first image in 2025. And now it produces around 20 terabytes of data a night. And you might be thinking, it's okay, we can just use machine learning for this. And yes, it's a useful tool which will help us analyze a lot of these data, but we'll always need manual data inspection to assess the quality of the data and to help us make new discoveries, the unknown unknowns. So a machine can't find something that it doesn't know to look for. We need our human perception for this. Using sonification could give us new perspectives on data, which could lead to exciting new discoveries. Sonification can also help us to represent complex multidimensional data, as there are several different parameters of the sound that we can use. There's pitch, there's loudness, there's tempo, there's something called timbre, which is like the characteristic of the sound, how we can tell different instruments apart. And these can all be used to represent different parameters of the data. You could imagine if you've got several different parameters, it becomes very difficult to plot on a graph. So this telescope in the bottom right is called DESI, the Dark Energy Spectroscopic Instrument. And the data that I'm using in my project comes from this, which I'm going to talk about a bit later. So going back to our overview, I've introduced what sonification is and hopefully maybe convinced you as to why it could be useful. And now I'm going to talk about the hidden black holes that I'm looking for. So, black holes. You might have heard of them before. These are regions of space-time which are so dense and massive. So the gravity is so strong that nothing, not even light, can escape from it. There are supermassive black holes at the center of nearly every galaxy in the universe, including our own. And we understand how smaller stellar black holes can form through the collapse of massive stars. But how these supermassive black holes form is still a mystery to us. Now, you might have seen this image on social media a few years ago. This is actually the black hole at the center of our galaxy, called Sagittarius A star. So this is a very small object on the sky and it's very far away. It's around 27,000 light years away. So to observe it, they had to combine the power of several telescopes from around the world to take this image. And it's so cool to me that you can take an image of a black hole. But I know people were sort of underwhelmed by this. As you can see, the suggested alt text that PowerPoint gave me when I was making this presentation is a blurry image of a red circle. I think that's fair, but it's still incredibly cool. And you might be thinking, hang on, you just said light can't escape from a black hole. So how come we can even see this blurry red circle? And that's a good question. So we can't actually see the black hole itself. That was the dark shadow in the middle of the image. But what we can see is material interacting with the black hole. So black holes feed through a process called accretion. And here we have an artist's impression of a black hole accreting. So as gas approaches a black hole, it's accelerated due to the huge amount of gravity. But because everything in space is spinning, it has angular momentum, which must be conserved. So the gas begins to spin around the black hole. So it gets shredded and forms a disk of material spinning around the black hole called an accretion disk. And as the gas orbits the black hole, it builds up a huge amount of energy due to the intense gravitational forces it's being subjected to. And this energy is released in a lot of radiation, which is what we observe with our telescopes. And when a black hole is accreting like this, we call it an active galactic nucleus. And these can be really, really bright. They can even outshine the whole galaxy that the black hole is in. And the brightest of these objects are called quasars, which is what I'm particularly interested in. We also see powerful jets shooting out of the galaxy, which are driven by magnetic fields. Now, if we think back to our multi-wavelength image of Centaurus A, which I showed you earlier, we can observe these powerful radio jets shooting out of the center of the galaxy. And we can begin to understand that there's an active galactic nuclei lurking at the center. These are super powerful, these jets and these objects, and they have a huge impact on the galaxy, including star formation rate in the galaxy and galaxy growth. So studying their behavior is important for us to understand galaxy evolution as well as black hole growth. And as a side note, you'll be pleased to know that the black hole at the center of our galaxy is not active. So we're not impacted by this extreme radiation, which extends way beyond the galaxy. So bringing it back to sonification, here's a sonification demonstrating radiation observed from a black hole going through a period of intense accretion. So you're going to see the black hole flicker, and if the stereo is working, you will hear in your left ear the visible light radiation, which is represented with a pitched chord. And in your right ear, you'll hear the X-ray radiation, which is represented with a white noise sound. So both of the sounds get more intense as the radiation is brighter, and you can hear how there's a bit of a stagger between the different wavelengths. There are flashing images in this video, I will warn you. Okay, so we've now covered sonification and supermassive black holes at the center of galaxies. So now I'm going to talk about how we can study them using a technique called spectroscopy. So as I mentioned before, we call these super bright active black holes quasars. which comes from quasi-stellar object. And that's because on the sky, these distant bright objects, they can look a lot like stars. So here's an example taken with the Hubble Space Telescope of a quasar and a star next to each other. They're pretty hard to tell apart. So we can use something called spectroscopy to identify these objects and learn more about them. So if you remember back to the rainbow of light that we can see, we can use a device in our telescopes called a spectrograph, which splits the light we observe from an object into these different wavelengths. So what we get is data which gives you the power of the light we observe at different wavelengths for an object. So we've got flux, which is like this power, and then we've got the different wavelengths. And from that, we get a lot of information about the object, and each type of object has their own signature in the spectrum. So here are some real examples of different objects in the sky and the different features that we observe. There's a lot of information we can learn from these about chemical composition, distance, star formation rate, motion, but for today, I'm just going to point out the distinctive features for these different types of objects. So you might notice there's these spikes in the spectrum at certain wavelengths, which we call emission lines, which demonstrate the presence of different chemical elements. With quasars, we see prominent broad emission lines and this sort of sloped shape downwards. With ordinary and inactive galaxies, we see narrow emission lines, and often the spectrum is sloping upwards from the lower wavelengths, the shorter wavelengths. And then with stars, we see absorption lines, which are similar to emission lines, but we observe them as dips in the spectrum instead of spikes. So these three types of objects all have distinctive spectra. What's the problem? So we have our typical quasar. We call these blue quasars because there's high power in the spectrum at blue wavelengths, which are the short wavelengths. But we don't always have a nice unobscured view of a quasar. Sometimes it's hidden and shrouded by dust, which reduces some of the blue light we would observe. So we call these red. We've observed some really interesting unexpected properties in these dusty red quasars, including enhanced radio emission. And there's theory that these could be an important phase of galaxy evolution. So having a complete census of these is key to helping us understand like the most powerful forces shaping our universe, really. We're really interested in these objects. But the dust makes these red quasars tricky to find. So if we look at the spectra, we can see the typical broad lines. So this is a typical blue quasar, but with the dust, it's reduced the blue light, which is these shorter wavelengths, and we get this different sloped shape, which is lower in the blue light and rises towards the redder wavelengths. So this makes it very difficult for our computer algorithms to find. They get confused and they mistake them for ordinary galaxies. And if we look back to our galaxy spectrum, you can see that actually now, yes, this is looking quite similar to our red quasar spectrum. And so because these red quasars are quite rare, they're very rare, it means we don't have the training data for our algorithms to try and find them. They get confused and they mistake them for galaxies. So in order to identify them and study these objects, scientists have spent hundreds of hours visually inspecting spectra to try and identify red quasars. So this is really time-consuming and tiring, and it's quite a challenging process. So we've learned what sonification is and that there are dusty black holes hiding at the center of galaxies. And we use spectra to try and identify them, but the dusty red quasars are hard to find and machine learning doesn't work. So this leads on to my research. Can sonification help us to find red quasars? Can it help make this manual inspection process more comfortable and efficient? This is what my research is all about. Exploring methods of sonification to see if it can help with this problem and potentially demonstrate a use case for sonification in astronomy research. Now, I will say this is all experimental and exploratory, so I don't have the answers yet, but that's what makes it exciting. So, I'm going to play you some examples, which are all real DESI data. And I've made all of these sonifications using Python code, which is just like you would make a graph. We've got a special package for sonifying data. So firstly, when we're inspecting our data, it's useful to get a quick overview of the spectrum to get an idea of the overall shape. As I mentioned, the slope is important, and if it has broad or narrow lines. So I mentioned earlier that the ear is good at perceiving changes really quickly. So here I've made some very short, they're 5-second representations of the data, where the data is played from left to right over time, and the flux or the power is being represented by the pitch of a note and the intensity of a white noise sound. So these are videos, the red line might lag a bit, we'll see. Have a listen and see if you can hear the difference between the different shapes and the broad and narrow lines. So this is a red quasar. And this is a blue quasar. I'll play the red one again. Now this is a galaxy which has narrow emission lines. See if you can hear the difference between the emission lines. I'm aware I made these sounds quite low, which might not be coming through the best through your computer. I apologize. So as I said, this is a really time-consuming process. So let's see if we can push it even faster. So now the sounds are just 2 seconds. I'll play them a couple of times. And this time it's just using a white noise, windy sound. So again, it'll be more intense when the flux is higher. Let's see if we can hear the difference of the shapes and the lines. I'll play it again. Now the blue quasar. And now the galaxy with the narrow emission lines. It's just a tiny, tiny blip at the end. And maybe you can't hear the difference, but this is what I'm going to test, and we'll see how fast we can get it. Something else that's useful for identifying spectra is looking at specific emission lines. So we know which wavelengths these should fall at based on how far away the object is. So the universe is expanding and objects are moving away from us. And this causes the light that we observe to get stretched and the wavelengths become longer, which is something called the Doppler effect, which you might have heard of. We can work out the distance of the object based on where these emission lines fall. But sometimes the computers get it wrong. And this is another thing that needs to be adjusted with visual inspection. So we can zoom in on the area and expect to find emission lines, the area that we expect to find emission lines, and listen to the data there and check if the computer got it right. So here I've got a specific group of 3 emission lines called hydrogen beta and oxygen 3. And when we listen to these, we can hear a distinctive rhythm. So these top 2 are from 2 different spectra where the distance is correct. So the emission lines are falling in the right place. and the bottom one is from where the distance is incorrect, and you'll notice the feature is missing. I will say these sounds are super quick, and when we were testing on Zoom, it didn't come through the best, but we'll see. I'll play them a couple of times and see if you can hear the rhythm of the emission lines. And then it sounds very similar to this one, which is the different spectrum. And then this one sounds hopefully different. When we compare it to this again. So that could be a really quick way of testing whether the computer's got the distance to the object right. So there's another sonification technique that we can use, which plays the whole spectrum at once, rather than evolving it through time. So this treats the spectrum of light wavelengths as a spectrum of sound frequencies. So the x-axis would now become frequency, which relates to the pitch. Higher frequencies are higher pitches. And the y-axis is the power at each frequency. So it's a bit like the volume, how loud each different pitch is. So when we get emission lines, these can be heard as specific pitches, and the rest of the spectrum you sort of hear as noise because it's lots of power at different frequencies. So we can listen to this technique here for a whole spectrum. So the whole sound is all of the data being played at once. And this spectrum's quite noisy. I'll play it again. So you can hear, maybe you can hear some pitches coming through, which are these emission line features. And now we've got the same spectrum, which has the same emission lines, but less noise. So maybe you can hear how the noise has been reduced, but potentially pick out the same pitches. We can use this technique to zoom in on emission lines again, and this can help tell us whether the emission lines are broad or narrow, which, as I mentioned, is an important distinguishing feature between quasars and galaxies. So this is a particular complex called hydrogen alpha, which has two emission lines. So we'll listen to a narrow version of it. So you can kind of hear a beating effect because the lines are very close together. And then we'll listen to the broad version of it. So you might notice you get the same beating effect from the two peaks that are there, but it's much noisier. There's less of a pitch because there's more different frequencies present in the sonification. So an important aspect of improving the visual inspection process is comfort. So I am working on these sound designs, and I appreciate that some of them are not the nicest to listen to. So an idea to help this is to map specific emission lines to specific pitches. So if you were listening to three emission lines, they could become three notes in a musical chord, like this, for example. So as I mentioned before, sometimes the computer miscalculates the distance to the object and the emission lines are not falling at the wavelengths that we expect them. So the whole spectrum gets shifted like this red line. And this means that the emission lines, when we sonify them, they're now going to be different frequencies. So the pitch has been shifted as well. So it might sound like this. And you could imagine tuning the spectrum like you tune an instrument, trying to get the emission lines to line up to where we expect them to be, which will help us calculate the correct distance to the object. So I'll play this second one again. And then if we compare it to where they should be, you might be able to hear the difference. And again, the ear is really good at distinguishing different frequencies. So this could be a really effective way to line these emission lines up. So I've thrown a lot of ideas out there, and my research is developing these techniques and testing which features could actually be useful to help improve the inspection of large data sets and help us find these hidden red quasars, hopefully. And in doing so, we might find more examples of red quasars which can help build up training data and improve our computer algorithms, which might make the process easier in the long term. Sonification is new to people, and maybe you were thinking, I can't hear the difference between any of these things. But just like visualized data, people need training in how to use it. So no one was born knowing how to read a graph, but we've all learned about it. So we will need to train people in how to use sonification. And there are millions and millions of spectra to search through. So this might turn into a citizen science project, which is exciting. So we might be asking you to help us listen to black holes and galaxies and try and find these hidden red quasars. And the great thing about sonification is you could listen to it while you're doing something else. You could be on the bus listening to black holes, which I think is really cool. Thank you very much for listening. I've covered a lot today about how we can use our ears to explore the universe, hidden black holes lurking at the center of galaxies, and how we can study them using spectroscopy. If you want to hear more sonification examples, I'd recommend you check out the Audio Universe YouTube channel. Thank you very much for listening.